Namaste children. Till now we have studied about the phenomenon of reflection. Now today we are going to learn about the phenomenon of refraction of light. To occur this phenomenon of refraction of light, this phenomenon is causing. You can say these are the causes. One is the medium should be transparent. Transparent medium should be there to cause this phenomenon of refraction. Second is optical density, not normal. D is equals to m by v, that is density is equals to mass by volume. This is normal density of the material. Here we need optical density. What is mean by optical density? Optical density is nothing but the ability of any medium to refract light is known as optical density. The amount of light, how much it is refracting that medium, that is its ability to do work. So what this optical device is doing, the work, undergoing the phenomenon of refraction. What is its ability? That is known as its optical density. Now what is mean by refraction? Refraction is nothing but bending of light rays, at the separation of two media, which is known as interface, at the point of incident, at the interface, at the point of incidence, the light ray which is coming from one medium and bending at that point and moving into the other medium is known as the phenomenon of refraction. Now, if you draw the normal, the angle, because it is coming, this is think that air medium and this is water medium. Suppose the ray is coming from air medium to water medium, it bends towards the normal. That means the optical density of water is more than optical density of air. So whenever a ray is passing from one medium to another medium, let it be medium 1 and this is medium 2. Then it bends at the point of incident at interface and travels in the other medium. When you are drawing a perpendicular to the interface, that is the separation of two media is nothing but the interface. There when you are drawing a normal, with the normal, what is the angle made by incident ray is known as angle of incident, and the ray which is making angle with the normal after refraction is known as angle of refraction. Now coming to the laws of refraction, the incident ray, the normal ray and the refracted ray all lie at the point of incidence on the interface on the same plane. Ratio of sine of angle of incident to the sine of angle of refraction is given color and to given pair of media, this ratio will be a constant which is known as refractive index and is designated by mu. Since both are angles only, it is a mere ratio. So there is no unit. Now, always whenever you are calculating refractive index with respect to some other medium, one medium and another medium, that is called as relative refractive index. If you are calculating the optical density of a medium with respect to vacuum, it is called as absolute refractive index. Now, whenever you are calculating the refractive index with one medium with respect to another medium, it is called as relative refractive index. And when you are calculating the refractive index with respect to vacuum, it is called as absolute refractive index. Suppose if you are with respect to air, water refractive index you are calculating, or air refractive index with respect to water when you are calculating, then it is called as relative refractive indices. When you are calculating air refractive index with vacuum or water refractive index with vacuum, then it is called as absolute refractive index. Now to it what factors the material medium. One is material medium. Then next is wavelength, lambda. Color of the light, material medium, directly proportional to the optical density of the medium, and it is inversely proportional to the wavelength, and also it depends upon the frequency. Observe this pencil, children. At the point of separation of the two media, that is this pencil is in air, the remaining pencil is in water. At the point of interface, that is separation of two media, it seems to be broken. That is, the ray will be, light ray which is passing through our eye, it will be bending and passing into the water. This is known as refraction. Otherwise, when you put a coin or a scale, it seems to be bulging. Now the spoon size you see when I am keeping, because this is also because of looking like bulging. This is due to refraction of light. So refraction depends upon the material medium, the color, that is the wavelength of the light, and the optical density, that is nothing but refractive index. For example, suppose you are taking, this is air medium and this is glass medium. When the ray is coming from air to glass medium, since the optical density is more, it bends towards the normal. Then the density of media, optical density, is nothing but refractive index, and it is designated by mu or n, small n. What it is? Mu is equals to sine, the ratio of sine of angle of I to sine of angle of R, which is also known as Snell's law. This is the second law of refraction, and it is also known as Snell's law. Since it is a mere ratio, there is no unit. Now, suppose a ray is coming from one medium and passing like this into the other medium. What is the angle of incidence? It is just 90 degrees coinciding with the normal. Then angle of incidence is 0. So angle R is also 0. So in this case, what will be the refraction? There is no refraction according to Snell's law. Now suppose if the ray is coming obliquely like this, when you are comparing these two angles are equal, angle I is equals to angle R, then also there is no refraction according to Snell's law. So what is refraction? Whenever a ray is coming from one medium and entering into another transparent medium, at the separation or boundary of two media, that is at the interface, at the point of incidence, it bends and moves in the other medium. If the second medium is optically denser medium, the ray will be moving towards the normal. If suppose the ray is going from glass medium to air medium, that is from a optically denser medium to optically rarer medium, then it moves away from the normal. So on what factors this mu, refractive index, depends upon? This is also depending upon the material medium, whether it is glass or water or air. Varies with the medium, it varies with it, and it is directly proportional to the material medium. Secondly, it also depends upon the optical densities of the media. So that is refractive index is depending upon their optical densities also. The density of the media to media. That is also, it varies with the optical media. So it is directly proportional to the media. Next it is depends upon the color or the wavelength, speed of the light when it is passing through one medium to another medium. Then refractive index is inversely proportional to the speed or velocity of the light. Now how can you find out n is equals to, suppose with respect to vacuum when you are doing, always n is refractive index of a medium is equals to speed of light in vacuum by speed of light in medium. So n is equals to c by v, where c is the speed of light in vacuum, where v is speed of light in the medium. This is absolute refractive index. And when you are not comparing with the vacuum, when you are comparing these two media refractive indices, that is known as relative refractive. The glass slab experiment. Now it is in cuboid structure. Suppose if you are observing, the faces will be rectangular faces. Now you place the glass slab A, B, C, D on a drawing board, on a drawing sheet, and mark the glass slab base. It will be a rectangle. Now mark the name as A, B, C, D. Now draw the perpendicular to one of the surface and just measure an angle of 30 degrees from this normal and draw a line and place two pins on that, P and Q. Name them as P and Q. And now place the glass slab and you view through these two pins and place two more pins on the other side, that is this side, seeing the base of these pins through this, and place two more pins this side and extend the line from here. Then draw a normal here also. Now join these two lines. Now this is known, this is RS, name this RS. And when you are observing all the through this or this side, all the four pins will be seems to be in the same straight line. This is known as angle of incidence and this is known as angle of emergence. And angle I is equals to angle E. This you are going to prove. This is R1 and this angle is R2. So R1 is equals to R2, and always angle R is less than angle I. Always angle E is greater than R only through glass slab. Now why they are looking like that? Now extend this line, then it will be parallel to the emergent ray. So this is incident ray, this is the refracted ray, this is the emergent ray. So now the extended incident ray will be parallel to the emergent ray. Then this distance between these two parallel lines is known as lateral displacement. This lateral displacement or lateral shift. This lateral shift depends upon the thickness of the medium, the thickness of the medium, and density of, that is optical density, refractive index of the medium. This depends upon refractive index of the medium, thickness of the material medium. This is and angle of incidence, angle I. And all these, when the thickness varies, lateral shift also varies. Refractive index varies, shift also varies. Angle I is varies, This is also varies, but lateral shift will be directly proportional to all these three. And one more dependent factor is the wavelength or color of the light ray passing through, or wavelength, that is lambda. Then when it varies, it is inversely proportional to, lateral shift is inversely proportional to lambda. That is the wavelength of the light ray passing through it. So, what is lateral shift? Lateral shift is nothing but the extended incident ray through the glass slab, which is forming a parallel line with the emergent ray. The distance between this emergent ray and the parallel and the extended incident ray is known as lateral displacement or lateral shift. And angle I is equals to angle E, and R1, angle R1 is equals to R2. Always angle of refraction is less than angle I or angle E, and always angle I and angle E are greater than angle R. This is about refraction. Now, not only this optical medium, another optical devices, which we will call them as lenses. Now, when you are observing one hand, how to remember mirrors. Now, you use your two hands. The Indian symbol, always when you are seeing the other person, what you will say immediately? Namaste. So, this is one kind of optical transparent medium, that is convex lens. We will call it as convex lens, and just you turn these two hands like this, and this is known as concave lens. So, other two optical devices, what we are going to learn is the spherical lenses, that is one is convex lens, the other one is concave
Namaste
lens.
children. Till now we have learned about the first phenomenon of light basing on the rectilinear property, that is reflection, that is bouncing back of light rays. Now coming to the refraction of light, the second phenomenon is refraction of light, that is bending of the light rays whenever they are changing a medium. Meaning of refraction is bending of light is nothing but refraction of light. So the bending of light rays when they passes obliquely from one medium to another medium is called refraction of light. So to occur this refraction, or what are the causes of refraction? One is the medium. What is the medium? It must be a transparent medium. Second is the optical density. Now, what is mean by optical density? Optical density is also known as refractive index. Now, in this chapter, we are going to learn the actual definition of refraction and what do you mean by refractive index and what are the laws of refraction, how this refraction takes place through spherical optical devices. The bending of light rays when they pass obliquely from one medium to another medium at the point of incidence at the interface is called as refraction of light. Now what is mean by interface? Interface is nothing but it is a boundary or surface of separation of two media. For example, see, the light ray is coming from the air medium and this is called as the interface, that is the boundary, that is the surface separation of the two media. Suppose this you are considering as water. So at the point of incidence, at the interface, the light ray bending and passing into the another medium is called as refraction. So this is air medium, this is water medium. So now what are the cause for refraction of light? One is medium, that is transparent. Second is the optical density. Optical density is nothing but refractive index. So the phenomenon of bending of light ray at the point of incidence at interface when it is passing obliquely from one medium to another medium is called refraction. What are the two laws of refraction? That is, the refracted ray, incident ray, normal lie at the point of incidence at interface lie on the same plane. Now, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant which is known as mu. This is constant for a medium for a given color of light. This is also known as Snell's law. Now, what is mean by Snell's law? The ratio of sine of angle to the sine of angle of refraction. It is constant. If you are taking, this is air medium, this is glass medium. The refractive index is more, that is called as optically denser medium. And if the refractive index is less, it is called as optically rarer medium. So when you compare air and glass, air is a rarer medium whereas glass is a denser medium. So for this, the ratio of sine of angle of this incidence to the sine of angle of refraction for this two media, that is air and glass medium, is a constant and it is designated by the letter mu. So this phenomenon is known as refraction, bending of light, and whenever it is coming, the incident ray is coming from a rarer medium to denser medium, it bends towards the normal. When it is going from denser medium to rarer medium, it moves away from the normal. Now coming to what is absolute and relative refractive index. Absolute refractive index is true. Now, what is relative? Relative refractive index is with respect to another medium. So, refractive index of one medium with respect to another medium when you are speaking, it is called as relative refractive index. When you are taking with respect to vacuum, this is correct, actual or absolute true refractive index. So if you are talking, that is air and glass media, that is relative refractive index. Suppose you are talking about glass medium with respect to vacuum, about the refractive index, it is called as absolute refractive index. So with respect to any other medium, when you are talking about the optical density, it is relative optical density or relative refractive index, or when you are talking with respect to vacuum, it is absolute refractive index. Refraction through a rectangular glass slab. Whenever light ray is incidenting obliquely on one of the face of the glass slab, a rectangular glass slab, it bends towards the normal and passes straight and emerges out through the other face of the glass slab, and when it is emerging, that is called as emergent ray and it is away from the normal. When you extend this incident ray through the glass slab, it will be parallel to the emergent ray. So the distance between the emergent ray and the extended incident ray is known as lateral displacement. Then the angle made by incident ray with the normal is called as angle of incidence, and angle made by the reflected ray with the normal in the glass slab is known as angle of refraction. So here R and R dash are equal and they are always less than the angle I. Angle R and angle R dash are equal and they are always less than angle I, and angle I is equals to angle E. This is angle of emergence. So when you are observing this experiment, suppose by pinning two all pins, seeing through the PQ of the glass rectangular cuboid AB and seeing through these pins inside the glass slab and pinning two other pins, so all will be seems to be in the same straight line. So after removing and drawing the normals and extending the incident ray will be parallel to the emergent ray, and the distance between this emergent ray and extended incident ray is known as lateral displacement. So angle I is equals to angle E, angle R is equals to angle R dash. Then when you compare the rays, see when it is coming from air and entering into the glass, it bends towards the normal, and coming out from the glass to air medium, it bends away from the normal. That means from here you can conclude that air is optically rarer medium when compared to the glass medium. So with respect to any other media, two media, a pair of media, you are talking about the refractive indices, that is called as a relative refractive index. So glass is a thick medium. This is normally density is equals to mass by volume, but here optical density is the ratio of sine of angle of I to sine of angle of R. It will be constant for a given color of light and for a given pair of media which are undergoing the phenomenon of refraction. Now this is whenever light ray is incidenting on a rectangular glass slab, it emerges out parallel to the incident ray and is laterally displaced. It moves from rarer to denser medium and then again to the rarer medium. Angle I is equals to angle E and angle R is equals to angle R dash, and always angle of refraction is less than angle I. Refraction at a planar surfaces. Now, how this refraction takes place? How can you apply the Snell's law? So now catching, for example, day-to-day applications, when you are observing, this is the plane. The light will be going from one rarer medium to another medium, that is air medium to water medium. So many rays like a cone shape it will be formed, which is bending and forming so many ripples like waves will be formed, and they will be forming a cone shape like and point towards the normal from rarer to denser medium when the light ray entering, and when it is entering from denser to rarer medium bends away from the normal, and where it is incidenting at that point of interface only it will bend. Again when it is going into the other medium, it travels in straight line. Now as already discussed, what is a refractive index? This is nothing but the extent to which light bends when moving from one medium to another medium is called as refractive index. Now mathematically it is depends upon the ratio of the speeds with which it is traveling in the two media. So the greater the ratio, more is the bending, and if the lesser is the ratio, less bending will be seen. So it is also the ratio of sine of angle of incidence to the sine of angle of refraction, and it is constant for a given pair of medium and for the given color. It is denoted by small n. So small n is equals to sine of angle I by sine of angle R. That is equals to speed of light in medium 1 by speed of light in medium 2. Suppose if it is not relative refractive index, n is equals to c by v. Angle. Now, basing on the phenomenon of refraction, another concept that is total internal reflection. What is mean by total internal reflection? Whenever light goes from a denser to rarer medium, it bends away from the normal. So the angle at which the incident ray causes the refracted ray to go along with the interface, that is, it coincides with the interface or parallel to the two media, then it is called as critical angle. After the formation of the critical angle, then the incident ray angle becomes more than the critical angle, then it reflects back inside the denser medium instead of refracting. This phenomenon of reflecting back into the denser medium instead of refracting due to the coincidence of the incident ray with the surface or with the critical angle, then the angle of incidence becomes greater than the critical angle and it bends, and instead of refraction it reflects into the same denser medium. This is known as total internal reflection. Example, mirages. Mirages is nothing but an optical illusion, that is in hot summer season when we are moving on a road, concrete road, highly polished road, we will be seeing that water is present in front of us. That is nothing but the hot air which is touching the ground creates a total internal reflection which is received by the by our eye, where our eye is placed in the cool air. Because of this, the reflection instead of reflection takes place and it forms as a mirage. This is one example. Now coming to what are the optical devices which are working basing on the phenomenon of refraction are known as lenses. Coming to the spherical lenses are refraction at curved surfaces. Whenever light is passing through the curved surfaces, it holds all the laws of refraction true. That means it follows the laws of refraction. That is, whenever light rays goes from rarer to denser medium, bends towards the normal, and when it is coming from the rarer to denser medium, it moves away from the normal. Then light incident ray, refracted ray and normal lie at the point of incident at the interface on the same plane, and angle of sine of angle of incidence to the sine of angle of refraction is a constant, that is nothing but mu or refractive. Spherical lenses are of two types. They are transparent media only, but one is the refractive surface is bulging outward, the other one is the refractive index is curved inward. The lens which refractive surface is bulged outward is called as convex lens, and which is inward, that is refractive surface which is inward, is known as a concave lens. Already we have studied about concave mirror and convex mirror. You can compare here convex lens with the concave mirror, whereas concave lens with the convex mirror. Concave mirror, how many types of images it is forming, same way convex lens also forms 6 types of images, since it is a converging lens, whereas concave lens forms from infinity to infinite only one type of image, that is virtual, erect, always diminished image, since it is a diverging lens. So concave mirror and convex lens are converging, whereas concave lens and convex mirror are diverging optical devices. In mirrors, reflection takes place. In lenses, refraction takes place. Now all the rays which are parallel to the refractive surface will seems to converge at a point which is known as focal point. Now coming to the important definitions in case of spherical lenses. One is pole. Here pole we will be representing exactly when you see this is pole. This is called as optical center. It is known as double convex lens. So this is called as optical center. Exactly the midpoint of this axis is known as optical center or optic center. Then, or it is also known as pole of the lens. Then principal axis. This is lenses are formed by two spheres. So exactly after passing here, exactly at the axis, the ray will be bending. Now from here, this is a transparent medium, so it will have two foci, that is two focal points. Now two focal points, when the rays are coming parallel to this principal axis and comes and refraction, after refraction converging, passes through the optical device and converges at a point on the other side of the lens, where the point where it is converging, it is called as focal point or principal focus and is designated by capital F. The distance between optical center and focal point is known as focal length of the convex lens, and the center of this sphere from where this part of the lens is formed is called as center of curvature, and the distance between the optic center of curvature is known as radius of curvature. Same way, suppose if you reverse the lens, all the rays will be coming from this side of the lens and converges at this point, this side. So this will have F1 here, F2 here. Same way, the center of curvature you will be designated by 2F1 and center of curvature this side 2F2. Now once again we will be seeing the related terms. So what is midpoint of the symmetric center or the axis of a spherical lens is known as optical center, and the line passing through the optical center and the center of curvature of the optical device is known as principal axis. Now para-axial ray is nothing but the ray very close to the principal axis is also known as para-axial ray, or which is, this is always parallel to the optical center. And center of curvature, the centers of the spheres from which the two spherical lenses are part, those are known as center of curvatures. Then focus, the point on the axis of a lens to which all the parallel rays of light are coming from and converging, and which are appear to diverge from a lens, that point is known as principal focus or focal point. Then the distance between optical center and the focus is known as focal length. Concave lens, the rays will be seems to diverge from that point, focal point, whereas in the convex lens, these all the rays will be focuses at a point. So concave lens is called as diverging lens, whereas convex lens is called as converging lens. Now the rules for the ray diagrams for the images formed by these two. Now as we have studied already in case of mirrors, the rays which are parallel to the principal axis always goes through the focal point, or the rays which are from the object passing through the focal point after refraction comes back as parallel to the principal axis. So rays which are parallel to the principal axis from the object will pass through the focal point or principal focus after refraction, and rays which are passing through the principal focus from the object after refraction goes parallel to the principal axis. These are the two rules, and the other is the ray which is coming from the object and passing through the optic center, it retraces. So the rays which are coming from the object passing through the optic center will be always retracing.